Welcome friends to my channel Niraj Kapase. So here we are learning microcontroller. So for the today's lecture we'll see IO port interfacing. So we'll see 8051 IO port, that is IO stands for input output. So in detail we'll see IO port interfacing. Okay, so those who have not subscribed my channel, please hit subscribe button for next upcoming updates. Okay, and also if you like this lecture, don't forget to hit like button. Also write your comments in the comment box. Okay, we'll start with the session. Okay, so what is IO? IO stands for input output. So this IO stands for input output, and these are the input output ports. IO ports are the input output ports. So 8051 is a 8-bit microcontroller. So it is having four 8-bit IO ports. So those are named as P0, that is port 0, P1, port 1, P2, port 2, and P3, that is port 3. It uses 8 pins all. So all are 8-bit. So it means all are having 8 pins. Like if you consider P0, we have P0.0 to P0.7. So we have P0. Again, this P0 starts with P0.0 to P0.7. So there are total 8 pins. If you consider this P1, again P1.0 to P1.7. If you consider this P2, we have P2.0 to P2.7. So all in between that there are P2.1, 2.3, 2.4 like this. And if you consider this port 3, again we have port 3.0 to P3.7. So in between that there are 8 different registers. So once you reset your controller, so what are the status of that? So all the ports, upon a reset, all ports are acting as an 0FF. So all ports are input ports. So all the ports are input ports on a reset. Okay. Then port 0 is also designated for 80 to 87. So here 80 to 87, these are the address and data bus, allowing it to be used for both address and data. Port 0 and port 2. Port 0 is multiplex, that is address and data, and port 2 is only for address. Also 8051 multiplexes both the address and the data to save the pins. So for that it uses ALE pin. So ALE stands for address latch enable. Okay, ALE stands for address latch enable. In the last lecture of memory interfacing also we have seen this in detail, what is the role of address latch enable, which indicates the port 0 which uses address or a data. So whenever ALE is 0, it considered a D0 to D7, that is it is a data. Whenever ALE is 1, it is an address. Okay, that depends on a ALE pin, whether you are using ALE 0. Whenever ALE is 0, it uses a data. Whenever ALE is 1, it uses a address. Okay, so this is about address and data. Then here it is a diagram where you can have all the ports and pin configurations. So we have already discussed this. So on this side we have port 1. So port 1.0 to 1.7, as I told, there are 8 pins. So it started with P1.0 to 1.7. Port 3 is multiplexed port, like multifunctionality port. So we can have port 3.0 as RxD, 3.1 as a TXD, 3.2 as a INT0. This is an interrupt pin. 3.3 is a INT1, T0 that is timer 0 pin, T1 that is timer 1 pin, write bar pin is there, read bar pin is there. Okay, so these are the different pins available. Extal 2 is there, that is crystal 2. Extal 1 is there, that is crystal 1. So over here we can connect a crystal. Then ground pin is there. Okay, then from on this side, on the right hand side we have P2.0. 2.0 will start from bottom hand side till P2.7. pin number 20, it is 2.7. So also this is multiplex, that is A8 to A15 address lines are there, and this is about port 2. Then we have PSEN bar, that is program store enable bar. We have ALE and a program bar, EA bar and VPP. Then port 0 will start from here. Pin number 39 is port 0.0. Okay, pin number 39 is P0.0 and P0.7 is here. and this is port 0. Again, port 0 we can read, you can read it is AD0 to AD7. So address and data, when that depends on again ALE. Whenever ALE is 0, it acts as a data. Whenever ALE is 1, it acts as an address. Okay, so this is about pin configuration of 8051. Here it is a VCC pin which is used to provide a VCC to the supply for this. So in all together we have 4 pins, 4 ports, that is P0, P1, P2 and P3. Okay, so P0, P1, P2 and P3. So each are having 8 number of IOs. Okay, so total overall 32 IOs are there. So at a time we can connect 32 IOs. Okay, so if you want to connect more than that IOs, then we need to do a multiplexer or demultiplexer. Multiplexer is required. Okay, next we'll see in detail study of a port 0. Sorry. So we here port 0. So port 0, it can be used for input and output. So we can use for both the activities this port 0 as an input or output. Each pin must be connected externally with a 10k ohm resistor. So that is pull-up resistor is required. So why pull-up resistor is required? Here it is a connection diagram. So we have port 0. So pin number 39 is there and so on. So we need to attach one pull-up resistor of 10k. Why pull-up resistor is required? Because this port 0 is open drain concept. So it uses open drain concept. So that's why this is due to the fact that port 0 is open drain. So here it is mentioned port 0 is open drain. Unlike port 1, port 2 and port 3. So external pull-up is not required for port 1, port 2 and port 3. Only for port 0 this combination is required, that is this external pull-up register is required, and the pull-up register value is of a 10k ohm. So you can use 4.7k, also you can use 10k. So both are fine. So open drain is a term used for CMOS chips. So open drain is a term used for CMOS chip in the same way that open collector is there for TTL chip. So this 8051 is a CMOS chip. That's why the open drain term is used, and port 0 is open drain. So because of that port 0, we need to attach external pull-up resistor due to it is a open drain. Okay. So this is about port 0. So 8 different resistors are required for this to attach, and those resistors acts as an pull-up resistors. Okay, so port 1 and port 2. So again, port 1 and port 2 are basic ports. So here port 2 is having a multifunctionality, like we have addresses on the port 2 as well. So 8051 based system with no external memory connections, both port 1 and port 2 are used as simple IO. So whenever we are using external memory connections, so port 0 uses port 0 and port 2 must be used, and these are used to provide a 16 bits of address. So upper address lines are available at this particular port 2. Port 0 provides lower bits of address, that is A0 to A7, whereas port 2 provides upper bits of address, that is A8 to A15. Okay, so this is again a special ports. Port 1 is a normal port, and you can use as general purpose IO as well. Okay. Next, so port 3, again port 3 is a special port. So port 3 can be used as an input and output. So it is a special port and it can be used input and output. The port 3 is having additional functionality. So additional functionality, what is this additional functionality? So it's having some additional functions like for serial communication. Okay, then we have external interrupt functions, we have timer functions, and we have read-write signals for external memories. So we'll see in detail. So P3.0 is located at pin number 10, and it is having additional function of RxD. So RxD stands for receive data. P3.1 is located at pin number 11, and it is having additional function of transmit data, that is TXD. Then port 3.2 is located at pin number 12, and it is having the additional function as INT0. So that is interrupt 0 pin. Port 3.3, that is P3.3, is located at pin number 13. Okay, and it is having additional function of INT1 bar. Okay, those are active low signals, that's why there is a bar on the top, that is INT0 bar and INT1 bar. Port 3.3 is located at pin number 14, and it is having additional functions of a timer, that is timer 0. P3.5 is having located at pin number 15 and additional function of a timer 1. those are reflected here, and those are extra hardware timers. And P3.6 is there, which is a write bar, again active low signal and located at pin number 16. This is used for external memory write. Okay, and P3.7 is the last pin of port 3, that is again RD bar. So again it is active low signal and it is located at on pin number 17. So again which is used for writing data onto the external memory, reading a data onto the from the external memory. Okay, so this is about port 3. Port 3 is having special functionality. So remember this functionality. So it's having serial communication, external interrupt 2 pins, then timers 2 pins, and read and write signal 2 pins. Okay, so this is very important for remembering this thing. Okay, you have to remember this thing. Next, very first program we'll see now. Program to send 55H. So we need to load the data 55H and AAH onto the port. Okay, so we need to send this data onto the port 0. So here I'm going to explain you the code. So instead of this, I will use Notepad for writing this. Discard this. Okay, so here it is the code. So we need to send the data, that is AA and 55H. So alternately it's going to turn on and off the port pins. So very first line you can use like this: move A comma hash 55H. So this is immediate addressing mode instruction. So this is immediate addressing mode instruction. So what this will do, this will loads accumulator with the value of 55H. Okay, then we are transferring that accumulator value into the port 0, sorry. Then after this instruction, port 0 contents are 55H. Okay, then we are jumping over the delay routine. So delay is just wait. So we can write a delay separately. Then we take another data, that is with this instruction we take another data into accumulator, that is 0AA. Okay, AAH. Again we are transferring that to port 0. Port 0 contents will be now 0AAH. Okay, then again we are calling the same delay routine. Okay, and we are just calling this as jump back. So back will be here again. So this goes on repeating the states. Okay, continuously it's going to blink the port and you will get alternate blinking effect on the port. We'll see the how actually works on the simulator. So I will open the simulator and I will write the code for you and we'll see that. So I will open a Kale IDE. So before that I will create one folder here, Kale demo. Just minimize this. Okay, so I'll rename the folder Kale demo programs. Okay, so I'm going to write the first program. So for that I will create inside the folder, that is port data. So give any name, that is program 1 or port data. So I've given the name as port data. Okay, now I will create a project. So how to create a project? Go to a project, start a new microvision project, and select your directory. So my directory is located on the desktop. So on the desktop, Kale demo programs from that port data. So I will give a name for the project as a port, save it. Then it asks me for which particular device I'm going to write a program. So select legacy device, and here 8089C51 I need to type. Okay, once I type 8089C51, you will get this here 8089C51. Select this and click OK. Once you click OK, if you are writing as embedded C program, then click on S. If you are writing assembly program, then click on No. So startup file is not required for the assembly program. So just click on No. Then go to file and new file. So blank window will open. So here I need to type a program. So first I will type org in a capital letters. I will type program org 4x0h as jump to main. I'm going to save it first, and so that my font will change. So prog.asm. So I need to save with the extension program.asm. Save it. So once I save, it changes the color. Then I need to write a main colon. So this is again directive. Okay, main label. Actually it is a label. So very first thing I need to take data into accumulator, move a comma hash 55h. Then I need to transfer that particular data into the port 0. So move v0 comma a. So this will transfer that particular data, and I need to wait for some time. So I can write a call delay. So I will use a delay, and I will show you the delay routine as well. Also I need to send a second data, move a comma hash 0 ah, and move to this port 0 again, move to 0 p0 comma a. Again I need to call the same delay routine, a call delay, and then let's jump to main again. So I need to repeatedly do this, so I will going to repeat this. So I need to write a delay routine here. So I will put a delay move. So I will take this label at in move. Suppose I will take a delay of into r0, move r0 comma has 05h. So only 5 delay I will take, so that you will come to know that how it's going to execute. DZNZ r0 comma here. So increment jump if not 0 to here. Okay, so I will give here for this. So it will decrement this, and once it is done with this, then it's going to return it and then end. Okay, so this is the program I typed, and I'm going to save this particular program now. Next step, after writing the code, I need to go to source file, right click on that source file, add existing files to a source group, select your ASM file. So select it, I have selected this program.asm, add it and close it. So here the program is available, that program.asm. Now you can build it. So once you build if errors are there, then these errors and warnings will be displayed. So code size is 21 bytes. You can change the frequency of this, go to this program, so that your timings are working properly. 11.0592. okay, so you can calculate the machine cycles as well. So this requires 1 machine cycle, this requires 2 machine cycles. So 2 into 5, that is 10 machine cycles it will take. So 10 microsecond is the delay for this particular delay routine. Okay, so I'm going to debug it now. Hit the debug button, click OK after this. Now from where you will get a port. So for that you need to click on a peripherals and go to IO ports and select your port. So select your respective port. So here I am sending the data to the port 0. That's why I need to select this port 0. So I will just drag and drop here port 0. Now I can do a step execution. So for step execution there is a key of F11. So I will just explore this, keep watch on this particular registers. So I'm just transferring this particular 55H into accumulator. So accumulator, if you move over the mouse over the accumulator, so accumulator address is 0E0. So you will get 55H will be transferred into accumulator. Now if I move this, so port 0 address is 80. So it's going to transmit, by default the port is FF. So once I reset the controller, the port 0 contents are FF. You can observe this. Okay, so again if I move it, so 55 will be loaded into the port 0. You can observe this 55 is available. Now we call a delay routine. So delay routine address is 010. So it goes to and it changes the program counter towards this. So it come here, the PC will load it with the 010. You can observe that 0010 program counter contains. Now it's going to load 05H into the R0. You can observe R0 will be loaded with the 05. DZNZ R0 comma here. So it's going to decrement this. Now it is 4. Again it's going to execute. The program counter goes on incrementing. Okay, you can observe that. It's a 13, 01, then it's come out, then return is there. So return means what? It's going to change the from this stack pointer address is 09. So this address will be loaded into the program counter again. So you can observe 08 will be loaded. So this is the address for the next instruction from this. So again my program counter is here. Now A will be loaded. Again a call delay is again 010. So again the program counter will be loaded with 010. You can observe this 010. Stack pointer is incremented. Now stack pointer is 09. So you can observe the data at stack pointer. Okay, stack pointer contains the next address of this jump main. Okay, if I compile it again, so it 5 times it will execute. R0 contains once it is 0, it returns back. So once it returns, stack pointer is again decremented, and the program counter is loaded with the previous address of next instruction, that is sjump main. So address is 00E. So this is loaded and sjump to main. So you can observe this. So my port data are here. So these pins are nothing but inputs, and on the above it shows the output. So there are two things. So here, if you want to give an input, give like this input. Okay, one cannot modify this while running the code. For that we need to set up that as an input in. Okay, so like this it's go on executing the things. All right, so I will stop executing this. We'll come back to the main program again. Okay, I guess you understood the code. Okay, so next program we'll see. Make port 0 as an input and read the data and send it to the port 1. So we are going to read the data from port 0 and we are going to send it to the port 1. So here for making the port 0 as an input, for making the port 0 as an input, so we need to send FF on to that particular port. Okay, so here it is a code for this. So move a comma has 0FF. So this makes the port accumulator loads with the value 0FF, and we are transferring that to the port 0. So port 0 contents are 0FF, means that port 0 is an input port. So whenever you are sending 00, that is output port. When you are sending FF, that is input port. Okay, so again this is the input port, so I am reading the data port 0 to accumulator, and then that accumulator data will be sent to the port 1 and sjump back. So this keeps on repeating the things. So I'm going to show you with the same program here. So I'm going to make the modifications in this program. So very first thing is take the data, move a comma as 0FH, then send it to the port 0. So port 0 acts as an input port. Then I need to read the port 0 and take that into the accumulator. So how to take that? So like this, move a comma port 0. Whatever the data I have available from port 0, I need to send it to the port 1. So I have done that. So before that, you can make port 0 port 1 as an output port by sending 00 there. So this is the thing you require. Again, this I need to repeat the things, like once it is input and once it is output, I need to do the things continuously. So I can write sjump to back. So my back will be here. So every time it's going to change, and every time it's going to execute the same thing, and it's go on checking the port 0 contents, and it's going to write that contains on the port 1. So okay, I have saved this. I have already coded the same. Compile it, go and debug. Now for this case I need to require two ports, that is port 0 and port 1. So I'm going to take a port 1 as well. Okay, if I want to give an input, I can give it from here. So if suppose my input is 0 C3, okay, sorry, my input is 03. So I'm going to step execute it. Now this port becomes an input port, so I'm going to make the port 0 as an output port, so it is output port. I'm going to read the data of accumulator into port 0. Okay, port 0 is a FF now. Now port 0 contents will be read. The port 0 contains this into the accumulator. Accumulator contains 03. You can observe here 03 is there, so that 03 will be transferred into the port 1. So you'll get port 1 as 03. Let's jump to back. Again, it's going to, if I change the input, my input is 07 now. So if I execute it, my input is 07, so 07 will be loaded. So if I change it again, my input is 04 now. So my output is 04 at port 1. So similarly, these things are repeating. Okay. All right, so we'll move forward for the next. Okay, so next program we can see as configure the port 1 as an input and read the data and send it to the R7 and R5 register of bank 0 alternately. So one time if we read the port 1, send the data to R7, and second instance if we read the port 1 again, then that data will be transferred to the R5. So we'll see in detail how the program is to be. So very first thing we need to make this that the port 1 should be input port. So by sending ff we can make that port 1 to the input port. So how to do that? So this is the instruction. We can make port move port 1 comma a. This makes and port 1 as an input port. So here I have wrote the comment as well. So if I want to write a comment, we can give a semicolon or double slash line. So both things are fine. So we can put double slash like this, or we can put a semicolon. So here I am transferring that port 1 data to the accumulator. Again I am reading the data from the port 1. So this instruction will read the data from the port 1. So move a comma p1 means what? The port 1 will be transferred into the accumulator, and then we are transferring that data to the R7. So R7 will be moved again the data to the bank 0. We have not changed the bank, that's why that will be loaded into the R7. Okay, then we call delay for some time, we'll wait for some time, and again we are going to read the port 1. So move a comma port 1. So again another byte of a data we can read from port 1, and that is transferred into accumulator. That data we need to move it to R5. So a to the R5. So again next data byte will be saved into R5. So here we are not repeating the data, we are not repeating the code. That's why. So here what we have configured, input is we are taking from port 1, and we are taking that into accumulator every time, and then that accumulator data will be transferred to the both the registers, one into R7 and another into R5. So every time we are reading this data from port 1. So R5 will be loaded, and R5 and R7 will be updated every time. Okay. So this is about configuration of this port 1 as an input, and loading into the memory, different memory locations. Okay, so we'll move forward and we'll see the next thing. Okay, so rewrite the code. Here it is. We'll read the thing. Port access directly. So we can access the port directly. Rewrite the code in more efficient manner by accessing port directly instead of using accumulator. What we have did here is we can read the port directly. Here it is a rewriting of the port directly. We can send the data to the port, like 55 will be loaded into the port 1, call delay. Again A will be loaded into the port 1 and again call delay. So the same thing we can complement it. The 55 means the value is 0 1 0 1 0 1 0 1, and AA means 1 0 1 0 1 0 1 0. So if you look at these two values, these are exactly complement of each other. So with this instruction we can complement the A. So instead of sending again AA, what I can do is I can load a accumulator of it 55, send it to the port 1. So port 1 contents are 55 now. Okay, and call delay. After that complement the A. The A is 55. So after complementing the port A will contains 0AA. So 0AA will be taken, and again I am moving this 0AA will be transferred to the port 1. So A is having 0AA now. Again I am calling delay, again complementing. So 0AA will be complemented, now A becomes 55. So this goes on repeating. So every time it transmits 55 and A, 55 and A. Okay, so like this we can write a code and we can execute the things. Okay, so we'll move forward. Here it is, sometimes we can access only 1 or 2 bits from the port. So like we can complement a single bit, or we can complement a single 1 or 2 bits in the port. So here we can have a complement 1.2 only. So only 1.2 is complemented. So here these are the port bits. So here port 0 is having 8 bits. So which are those? So port 0 is having P0.0 to P0.7. Similarly, port 1 is having P1.0 to 1.7. Similarly, port 2 is having 2.0 to 2.7. Port 3 is having 3.0 to 3.7. So we can have port 0 bits, D0 to D7 bits. Okay, so here I can write complement P1.2 means what? It complements only 1 bit from this port 1. That is second number bit. So this bit is complemented only. Okay, another variation of a code of a program, set bit 1.2. This sets only for P1.2. Again, clear 1.2 means it clears only 1.2. So this will do only for 1 bit. Okay, so single bit instructions are there. For this we are going to use single bit instructions. Okay, single bit instructions are used for clearing and setting up a single bit instruct. Okay. Here, write a program to generate a square wave with a 50% duty cycle without using a timer, just by complementing a single bit. So we can set a bit and we can reset a bit and it will generate a square wave. And we are calling a fixed amount of a delay in between. So how it will do? So once we send, suppose this is my P 1.0 and I have sent one output. So one is available constantly. Okay, after some delay I make it 0 and I will call the same amount of delay. Again I will make it 1, again the same amount of delay, make it 0, again I will call the same amount of delay, again make it 1, call the same amount of delay. So this you can observe that this is a square wave. So this is 1, this is 0 data, this is 1 data, this is 0 data, this is 1 data, so on. Okay, so like this we can have the 50% duty cycle means that on time and off time. So here on time and off time are equal. Okay, both the on time and off time are equal, having the same length. We can toggle P1.0 to have with the same time delay between each of the states. So here we can do like this: set B P1.0, call delay, clear P1.0, call delay. So similarly we can write one instruction for this as well, CPL 1.0, and I'll call delay a jump here. So with one instruction we can do this. So complementing 1.0 means what? It's going to update the value. So here it is the code and here it is output. So I'm going to show you this with a scale where you can observe this waveforms and all. I will discard the things. I will go and open the scale. I will stop simulating this. And in the same program I will update the thing. So here first of all I will move P 1.0 comma okay, so instead of move I will use set B. Call the delay routine, clear P 1.0, sorry 1.0, call delay, then as jump to main. So continuously I want to repeat this. So I will call a delay. So I'll call a little bit more delay now. So you can observe the delay and you can observe the waveform. So move R0 comma hash 0 FFH, move R1 comma hash 0 FFH, DJ and Z R0 comma here. My here label will be here. Okay, so move this back. Then for the second time move DJ and Z. So this is a repeated delay. So here 1 I will put, so my here 1 will be here, colon delete. Okay, so after doing this I will return from this and then I will put in routine. Okay, so this is the thing. I'm just going to complement the things. Okay, and I'm just repeating the steps. So I'm going to save this code. Where to observe this waveforms I'm going to show you. So I will compile it. 0 error, 0 warnings. I will debug it. So it's having a logic analyzer inside this. So you can observe the same thing on a port bits as well. Okay, so if I run this, so you can observe the toggling of the bit on the port 1. Sorry, so delay is too huge. So I'm going to decrease the delay amount. So I'll make this for just 0.5 times. So here I will make R1 and here I will make R0 to here 1, R0 to here 1. So 5 times it's going to execute. Delay, continue. Okay, run this. So you can observe that FE, so this bit is toggled. Okay, so you can observe this on a waveform. So if you want to observe the waveform here, so I can go to here logic analyzer window. So here it is a logic analyzer window. I can maximize this window. Okay, so here it is. I need to set up this logic analyzer window. In this I need to add a particular pin. So I'm going to type the pin here, P, whatever the P 1.0 I have typed. So close this, so you can observe that. Okay, you can observe here it's going to change the thing, and you can observe a square wave, very short square wave is there. So you can zoom it, zoom in, it's auto. Yeah, if I make auto, you can observe the 50% duty cycle here. Zoom in, zoom out is there, grid is there, 10 millisecond of a grid. Then we can have auto, undo, stop, clear. If I stop it, you can observe the square wave. You can observe the timing cycle as well. We can count the timing cycle. We can traces are there, so we can trace from here to here. This is a full machine cycle, so I can trace it. Okay, so total time you will get from here to here and all. So that thing you can trace, you can jump to code, you can trace, you can have a cursor set up, so you can put a cursor here as well. So cursor from here to here, so that thing we can do. We can have put amplitude, we can have show cycles. So here there are different cycles available. It will show the cycles, signal information it will show, it will amplitude, it will show what's the amplitude, where it is at actual value 1 and 0. So many options are available in the logic analyzer. So like this, you can use a logic analyzer to get the output of zeros and ones. Okay, so I will stop simulating this, come back to the program. Okay, so there are some single bit instructions available with this particular microcontroller, that is 8051. So we have set bit, set b bit. So this sets the bit. So this is for setting the bit. Then clear the bit. There is no b available in this clear. So CLRO only the instruction. CPL stands for complement the bit. Okay. Then there are the jumping instructions. JB bit comma target. So jump to the target if the bit is 1. So if the bit is present, it will jumps to the target. JNB bit comma target. So it will not jump to the bit when the bit is 0, bit is clear. Jump to target if bit 1 or clear a bit. So JBC means what? Jump a bit and clear the bit. After jumping, it clears the bit. Okay, jump a bit then clear. So both the things in one instruction, like clearing the thing and clearing the bit and jumping with the bit. Okay, JBC. So these are the single bit instructions. Next, checking a single input bit. So how you can check the single input bit? So for that, either we can use JNB or JB, jump bit or JNB. So here JNB is used for jump if no bit, and JB is used for jump if bit. These instructions are widely used for single bit operations. So single bit operations are very rapidly used in the programming. So it allows you to monitor a single bit, like if you want to observe a single bit, and if you have attached one sensor to a single bit, and if you want to monitor that. Suppose if you attach one switch, and if you want to monitor the switch, once the switch has been pressed, you need to turn on the LED. So for that, we need to monitor that particular bit. So decision is to be taken with based on the result of this particular bit, whether it is 0 or 1. These two instructions can be used for any bits of input output of port 0, 1, 2, 3. So port 3 is typically not used for IOs, either single bit or a byte wise, but you can use this particular instructions, move a comma px. So here px is the port value, that is move a comma p2. Then JNB px dot y. So x is your port and y is your bit. Okay, so JNB 2.1 comma target. So if there is no bit on 2.1, it jumps to a target. JB jump bit to the target. Jumpy bit, that is JB P1.3. If there is a bit on P1.3, it will jump to the target. Move C to the move C to P2.4. So it P2.4 will be copied into carry. So this will copies that P2.4 into a carry. So like this it will do. It copies the P2.4 data into the carry. Copy the status of P2.4 into the carry. Okay. So like this we can use these particular instructions. So we'll see one program for monitoring the input bit. So write a program here. I will read the things. Write a program for performing the following things. So what are the things? Keep monitoring the port 1.2 bit until it becomes high. So once it becomes high, we don't know when it will become high, but we need to monitor that P1.2. Once it becomes high, write the 45H value to the port 0. So we need to send 45H to the port 0 and send high to low pulse on P2.3. So again, one pulse will be sent to port 2.3. So here we can monitor this. So this bit is an input. So how to make an input bit? By sending 1. So I can write set B P1.2. This makes the P1.2 as an input. Okay. So here I can write move A comma 45H. This data I need to transfer to the port 0. So I have taken this into accumulator. Okay. And this instruction JNB P1.2 again. So this instruction will wait till this bit goes to high. So JNB P1.2, jump if no bit P1.2 again. So get out when P1.2 is equals to 1. So move, next instruction is move the data into the port. So I am writing move P0 comma A. Then I need to send one pulse. So how to send the pulse? Set B P2.3 and clear P2.3. So this will set and clear. So high to low transition. So this makes like this transition. So this makes like this transition. There is a high pulse, then low pulse, then again that's it. Okay. Right, so another program for checking the IOs. Assume that P2.3 as an input, so we can make P2.3 as an input, represent the condition of an oven. It goes high, it means that oven is hot. Okay, the monitor the bit continuously. So we need to monitor the bit continuously. So we need to use JNB or JB. Whenever it goes high, so high means we need to use JNB. Sends the high to low pulse on the port P1.5 and turn on the buzzer. So buzzer is attached to P1.5. So here I'm just monitoring the thing. Here JNB P2.3 here. So keep monitoring the flag, monitoring the for a high. Then it sends P1.5 set and then clears the 1.5 and a jump here again. So it turns on the buzzer. So buzzer is attached to P1.5. So these two lines are for buzzer to turning on and off the buzzer. Okay. So again, one more thing, we can send a parallel data onto the port. Switch is connected to P1.7 and write a program to check the status of a switch. Okay, so to check the status of a switch, if switch is 0, send N letter to the port 2. If switch is 1, then send Y letter to the port 2. So here is the program, set B P1.7. So we have made the port 1.7 as an input pin. Then again jump a bit to over. Okay, jump a bit P1.0 to over. So over means what? Whenever there is a bit available, so whenever there is a bit, I can send Y. So here move P2 comma Y and jump to again if there is a bit, then it will send Y. If there is no bit, then it sends N, and again I'm going to jump it to again. So you can write these labels many times. Okay, you can write these labels many times and keep monitoring this particular thing. So I'm going to show you this particular code, the Kale. So I'll open the Kale, I will delete the previous code. Okay, so what is the code? So I need to check the P1.7 and check the P1.7 and then jump it based on that. So first of all, make P set B P1.7. So this makes an input port. Then I can monitor that JB P1.7 to next. I will put a next here. Okay, so I will put again here. So I need to repeat the steps. So I will put again and I'll put a next. So whenever there is a bit, it will jump. But whenever there is no bit, I can write to the port. Which port I need to send? Port 2. So I can write port 2 comma hash N. So whenever there is no bit, I can write N onto the port 2. Then I jump again. AGAIN. Okay, and I can have a next here. Means what? I can send Y when there is bit. So I can write move P2 comma hash Y. So like this I can write, and again I need to write s jump to again. So I need, this label is given, so it will jump to the same location. So done with this, now I can compile it, and I need to change the status of this, and I need to syntax error. So just double click. So comma is missing, that's why JNB 1.7 comma next. So comma is required, that's why it gives me a syntax. Zero error, zero warnings again. So I can go to a debug. So I can take this port 1. So I don't want this analyzer, so I can close the analyzer from here, hide this analyzer. Okay, so I can move this up so that I will get the code here, and I can monitor the port 2. So I will take a port 2. So port 2 is available here, port 1 is available here. So I can step execute. So port 1 this set, so my value is 1 now. So 1 means what? It sends Y. So it sends Y. So this is Y actually. So if you observe this, port 2 contains 0x59 is the ASCII value or hex value of Y. Okay. So this is a Y. So you can observe here Y character under this location. So on the stack we have Y location. Again it will go back, it will do continuously these things. So once P1.7 is clear, so I can give an input clear. So at that time this P1.7 is 0. So it goes and send n. So n is written. So you will get n here. Okay, 40. 40 is n. So again it's clear. So it will not execute this y. So okay. So whenever it's 1, at that time it's go on executing y. Okay. Similarly, it goes on executing this thing. Alright. So clear about this. Okay. Next. Program for LED and a switch. So a LED and switch connected to P1.0 and LED is connected to P1.2.7. So write a program to get the status of switch and LED and send it to the LED. So I can copy the contents of P1.0 to the carry bit, and I can write that carry bit into the 2.7. So how we can write a program. So this program I already explained to you this thing. Okay. I can copy the code from here. Okay, so we have here the microcontroller. Okay, so we have here a microcontroller, and the connections diagram is like this. So we can have P1.0 is connected and LED is connected to P1.2.7. So P1.0 is available here and P2.7 is available here. For the 2.7 I have LED connected. I'll make this ground. My LED is available here, and one switch is connected. So I can connect the switch over +5. So my switch is available, and I'm going to connect it to the this plus VCC is there, P1.0. So this is 8051. I'm going to explain you the code. Set P1.7 means what? This makes this sorry, here it is 1.0. So here it makes this P1.0 as an input. So I can copy the P1.0 contents to the port C, a carry flag, carry bit. So move C, comma P1.0. So if it is a clear, means if it is switch is not pressed, then that LED is off, because I am sending the same carry bit to the P2.7. And whenever it is pressed, so VCC is available to this, then LED is on. So every time it's go on repeating the steps. Okay, so like this we can program and interface the switch and LED. So this is one of the lab. We can perform this in the lab as well. Okay, all right. Next we can see read and modify. Read, modify and write. For that we can use different instructions. So I'm going to elaborate those particular instructions. Reading a port as a latch. The instructions read the port latch normally, read the values. Okay, the perform an operation when rewrite it back. Also we can rewrite it back as a port latch. Okay, so we can use ANL. ANL is the ending instruction. ANL P1 comma A. So it will add the value with the accumulator. ORL is the ORing instruction. This will OR the port. Then we have XRL, that is XOR instruction. We have JBC, that is jump a bit and then clear. We can check with this bit P1.0, and then if it is set, then we can clear it. complement the p so complement one of the bit, increment the port 1, so this will increment the port 1, this will decrement the port port 2, dznz port 1 comma target, so decrement jump if not 0 the port 1 comma target. So we can have move p 1.2 with a carry flag, we can move it to any of the port pin, then clear 2.3, we can clear it out, and we can set bit 2.3 as well. So here x is port 0 1 2 3 and of the port this, and y is 0 to 7, so these are the bits, y is bits and x is the port, so x values are 0 1 2 3 and y values are 0 to 7. Okay. All right, so this is IO pins controlling states. So what is there inside in microcontroller? So we have internal output input output registers available, those holds the data. Then we have a special function registers, so those are updated with this particular internal register. And there is a port register available, so with this port register that data will be transferred into the buffer first, and then that buffer will be loaded with the appropriate special function register. So we can attach any of the inputs and outputs, we can configure separate bits accordingly. Okay, so we'll end up with this input output lecture session. Again, how you feel this lecture, just if you like this lecture, just hit a like button, and also write in the comment box about this lecture. And those who have not subscribed my channel, please press the subscribe button to get next upcoming updates. Thank you for listening.